How we doing, friends? Uncle Lee back here with you with a little discussion about the cosine ratio as being a function, of some angle measure. Very important topic in our study of trigonometry. Let us not forget where the cosine ratio came from, and that's where we're going to begin. And then we're going to end up looking at the graph of this cosine ratio as being a function of an angle measure. We're going to graph this thing end up graphing it on an XY coordinate axis. But let us begin by recalling the basic geometric definition of the trigonometric ratios. Very important. Learn this in geometry. But today we're only going to talk about the cosine. I'm going to let y'all do your sine graph yourself, and to make the conversion from your sine ratio to a sine function and the graph of the sine function, which you should be able to do following this discussion about the cosine. But if you recall the geometric definition of the cosine function was very simply the adjacent over the hypotenuse, the adjacent length divided by the hypotenuse. Hence the word ratio. It is a ratio of the adjacent side of an angle divided by the hypotenuse. And keep in mind, when we were in geometry, this guy here was always an arbitrary angle measured in degrees between 0 and 90. It had to be between 0 and 90 because we only talked about, when we were given the geometric definitions, we only talked about this triangle as being a right triangle. That's the cosine measure, the cosine ratio of an angle adjacent to the hypotenuse. And then where did we go? Well, and then we had this discussion about what in the world is a radian, because we wanted to go from degrees to radians. So we gave a nice definition of radian, well, not a nice definition, the definition of a daggone radian. And what the heck is a radian? A radian was simply, had to go back again to our geometry discussion of circles and central angles. A radian, one radian was defined to be the angle measure such that the length of the arc was equal to the radius of the circle. That's how we defined a radian. Not going over that again, that was a previous discussion. Radian. And now we got these angles. Hey, now they're not degrees anymore. We can talk about a radian being a real number. It's a real number. Very important with where we're ending today. And then what did we do? Then we talked specifically about a circle that had a radius of 1 unit, i.e. the unit circle. And we not only talked about that, we took that unit circle and we translated it to the XY coordinate axes. We took that unit circle with radius 1, we translated it until the center of that circle was right smack in the origin of our XY coordinate axes. And then at that point, then we started looking at, oh yeah, radian, angle measure. And then we started thinking, oh yeah, theta can be greater than 90. In fact, what we discovered, because of our definition of a radian, radians, these angle measures, we discovered for the first time that they can go on and on. They can get infinitely big. And in fact, now we can start talking about negative angle measures. Yes, very important to where we're going. We can take angle clockwise around here, and we can let theta be this angle measure that we're now measuring in radians, in real numbers, can be negative also. And so we have no bound on our angle measure, on our radian measure. Our radian measure, our angle measures, this real numbers, this guy right here can be anywhere from negative infinity to infinity. We can go clockwise around that as however many times we want. We can go counterclockwise, however, yes. So the bound of our radian, our angle measures, negative infinity to infinity. That's nice. It was very nice. And then we specifically, when we translated this unit circle so that the center was the origin, the center of the unit circle was the origin, then we defined very specifically the cosine of that angle and the sine of that angle. And how do we define that? We define the cosine of that angle to be the x-coordinate of a point on the unit circle. The y-coordinate was defined to be the sine of that angle. Whatever that angle is, the y-coordinate was defined to be the sine of that angle, given that we were on the unit circle. And we're only talking right now, for this discussion, cosine. Cosine is defined to be the x-coordinate of a point on the unit circle. Do we have a bound on this cosine ratio? Do we have a bound on that? I don't know, but then what was the next thing that we did? We'll talk about this later too. But what was the next thing that we did? Then we looked at this concept of increments, specific increments on the unit circle. Nice increments, nice radian increments. Oh, like halfway around was pi, because all the way around, we're on the unit circle there. We're on the unit circle. Let's make sure that we're on the unit circle by signifying that that point is 1, 0. And then we looked at all these, 5 or 6, 1, 6, 2, 6, 3, 6, dot, 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 1/4, all that. And then these were specific increments of the unit circle. We did that. Increments of radian measure. These are all angles. Angles, pi over 6 angle, pi over 4, 1/3 pi, 2/3 pi, 7/6. And we kept doing that. And then we went backwards also. Negative 1/2, negative 2/3. But these were very specific increments that we talked about. They could be any, well, keep in mind that theta, our restriction on theta, we had no restriction on theta. These was anywhere between negative infinity and infinity. It just so happened that it came out really nice because 36 to 90, 45, 45, 90, that we talk about sixths, fourths, and thirds of pi radians. Review. And then we actually, what did we do? Then we actually, for those specific values, we looked at, and keep in mind I'm only looking at the cosine values, the x values of those points. And I'm only going to look at those x values. You know, if theta was 0, the x was 1. Pi over 6, the x was square root of 3 over 2, and the cosine of pi over 4 was square root of 2 over 2, the cosine of pi over 3, 1/2, the cosine of pi over 2, 0, the cosine of 1/3, 2/3 was negative 1/2, 1/4, 2/4, 3/4, cosine of 3/4 pi was negative square root of 2 over 2, the cosine of 1, 6, 2, 6, 3, 6, 4, 5, 6, cosine of 5, 6, 1, 6, 2, 6, 3, 6, 4, 6, 5, 6, the cosine of 5/6 pi was negative square root of 3 over 2. The cosine of pi, negative 1. And then what happened? These x values, for these important increments on the unit circle, they just kept repeating. The x's are negative. Negative square root of 2 over 2. Negative 1/2. 0. 1/2. Square root of 2 over 2. Square root of 3 over 2. So the x values just started to repeat. Well, that should, if you think about that, that's going to give us a bound of the output of this function that we're talking about. It has to. What function do we want to talk about? We want to talk about this guy right here. Where was he? We want to talk about this function. that's going to give us a bound on our output. Our input had no bound. Our input theta could be anywhere from negative infinity to infinity, but this discussion that we just had there, that's going, where in the heck were we? That's going to give us a bound then on our output, won't it? Sure it will. The bound on our output has to be between -1 and 1. It has to be. It's always. The output, the x values, because of the way we find cosine, x coordinate, the unit circle of an angle measure that could be any positive or any negative, our output's going to be between -1 and 1 of that cosine function. It has to be. Has to be. That's nice. So now I'm going to get ready to graph this function here in a little bit, but just slow your roll for a moment. So I have f of theta. I have the domain, if I want to talk about this theta, this function, and I certainly am, I'm talking about it now, that's why I want to, I'm not going to, I'm going to. The domain, and you know, since we're talking about that, we were in this class, when you talk about functions, the first thing you do when you talk about a function, you consider its domain. And then you have to consider its range. We've already discussed the domain is going to be theta such that theta is any daggone real number. And now we can actually talk about the output. We can talk about this output of this function as being between -1 and 1. The range of that function that I want to talk about is going to be between -1 and 1. That's interesting. Seems limited. True, though. But now here comes the part that people struggle with. Well, if I'm going to graph this function, and this is the part that some students have a hard time wrapping their head around. It's the part that some teachers maybe gloss over or leave out. If I'm going to talk about this function, if I'm going to graph this function, I'm going to graph it on another x, y coordinate axis. Everything we do, well, not everything, but 95% of what we do is going to be on the x, y coordinate axis. We're going to graph polar points on the x, y coordinate axis. We're going to talk about bugs moving parametrically on the x, y coordinate axis. So we're going to talk about these trigonometric graphs of these trigonometric functions on the x, y coordinate axes. And when we talk about functions, right now anyway, the y, the vertical axis, is going to be our dependent on the x independent. And so our y is going to be our vertical output dependent. Our output's going to be cosine, so our y value is going to be -1 to 1. I thought the cosine was an x value. It's the x value of the unit circle. But as soon as we start talking about it as being a function that we're going to graph on the in xy land, y's output, theta input. In a little bit, we're going to talk about theta as being x. Our range then is going to be from -1 to 1 because that's the bound of cosine. That is the bound here. From -1 to 1. That's why this is. Well, heck, let's start graphing this. Let's think about this graph, y of cosine theta. This graph of function, this graph of this dude right here, of this function of theta, cosine theta. Let's talk about that graph on the x, y coordinate axes, where the independent, the horizontal axis, is going to represent our theta values, and we're going to let them be x's since we're in xy land. Oh, and that's nice because, you know what, when we're in xy land, x represents real numbers. Y's are real numbers. Well, can we measure? Well, yeah, we can. This is the reason why we convert our degrees to radians, so that we can graph these guys on an x, y real number coordinate system, or the independence real numbers, the horizontal real numbers, vertical real numbers. And our angle measure are in real numbers there in these nice things that we call radians. And if what I'm going to do is I'm just going to look at that output, that cosine, one time around the unit circle, i.e. from 0 to 2 pi. And I'm going to divide that into fourths, just for fun, just to get a good idea of what's going on. I'm going to go from 0 to pi, half of that's pi, fourth of this 1/2 pi, 3/4 is going to be 3/2 pi, of 2 pi. And I'm going to look at my outputs. Well, my output, then my graph, my cosine, my function, my output is going to fluctuate between -1 and 1. And where am I? Let's see here. Don't want to go there yet. But where am I? I got these points. Where am I if theta is 0, cosine of 0 is 1? That's why I'm there. And if I go to pi over 2, cosine of pi over 2, recall your unit circle, the cosine of pi over 2 is 0. The cosine of pi is -1. The cosine of 3/2 pi is back here at 0. Think about your unit circle. That's where I'm going, right here. Think about your unit circle. And I'm going around the unit circle. And then if I'm at 2 pi, I'm back at 1. Theta is all real. Theta does not get chopped at all. The theta values are continuous. So all I really have to do, since this is a continuous function, and we know what a continuous function is, smooth. Well, not all continuous are smooth, but this one is going to be smooth. I can just graph that dude. Well, what happens between these values? Well, what does happen between these values? Hey, what are these lines? These are those other important outputs, those other important x-coordinates on the unit circle. 1/2, square root of 2 over 2, square root of 3 over 2, square root of 4 over 2, i.e. 1. -1/2, negative square root of 2 over 2, negative square root of 3 over 2, -1. And I could actually, do I do it here? Yes. And that's the graph of cosine for one time around the unit circle from 0 to 2 pi. And hey, what maps to this 1/2 right there? What goes to 1/2? Well, what does go to 1/2? What value is this? What radian value is this? You can check that out right there. Well, what goes the first time? What goes to 1/2? Pi over 3. What goes to square root of 2? Pi over 4. What maps to square root of 3 over 2? Pi over 6. But to get this graph, I simply looked at these x values and, where was I up here? These increments on the unit circle. And what would I like to do now? Hey, theta goes from -infinity to infinity. Let's graph the whole daggone function of cosine. Let's graph the whole thing, why don't we? Let's do one period from, oh, okay, that's going to be 2 pi right there. Make sure that this is 2 pi. This is pi. This is 0. Hey, what's this going to be? Negative pi, negative 2 pi. And what happens with our cosine graph? We see one time around the unit circle, another time around the unit circle. What happens to the x values? They just start to continue, to repeat. They follow the same period. Oh, hence the word periodic function. And how long does it take for these x values to begin to repeat? 2 pi, hence the period of cosine pi. So take a deep breath and think about this. And think about where these y's came from. These outputs came from the x coordinates of the unit circle. These inputs came from angle measures. And I can call, since I'm graphing it on the xy coordinate axes, I can take y as a function of x, where the x's are radian measures and y are the outputs. What I'd like for you to do is to come up with the same discussion for the graph of this function right here. And here's a nice one. What would happen to this function? What if I wanted to graph this function? And there's ways that we're going to talk about this to make this easy to look at. But think about this function also from a circular perspective, from a geometry circular perspective. What has to happen with this particular function? This is going to follow the discussion, both of these follow this discussion that we just had. So, take a deep breath. The study of cosine and sine functions are amazing. Catch you on the flip side.